Okay, good morning. Just wait for a few more minutes. You see that there are only about 30 students. Session. So, any questions? Most likely, the tutorial 2 marks will be released today. Okay, the TAs have completed the evaluation. We have to just consolidate the marks and then share it with the students today. I'll also send the solutions. Please have a look at the solutions first, and then you may send the request for the regrading. Okay, so don't send the regrade requests without looking at the solutions. And the distribution of the marks for the different parts of each question are also indicated in the solution sheet. So please have a look at that and then verify with regard to the marks for whatever you have answered. Okay. So the TAs are asked to do the evaluations as per the distribution of the marks as I have suggested. Okay. So unless there is really a serious discrepancy, right, please don't send the request for regrade. Okay. If you have any issues with the solutions themselves, you can write to me. Okay, and then I will respond to that. Okay. Yeah. Any other questions? Okay, let's get started. I'm not sure why there are only about 40 students. The classes for the other courses over. I'm told that the class for the PDS course are over. What about the other courses? Okay, I'm not sure. Okay. So let's continue our discussion that we were having in the last class. Yeah, after having looked at how the machine code gets generated, what we are trying to understand in the last class is how this machine code gets executed in the typical processor. So for that, we understood what are the different components in the CPU typically, right? And what are the modules outside the CPU that the CPU has to interact. So typically, we've seen that in order to fetch the instructions, the instruction memory is accessed, right? And the program counter has the address of the next instruction to be fetched that will send to the instruction memory. Then the instruction that's fetched from the memory will be stored in the instruction register, the content of which will go to the control unit or the instruction decoder, which basically takes the responsibility for sequencing the different operations in the execution of the instructions. And the main responsibility of the instruction decoder is to generate the appropriate control signals at the appropriate points of time to make sure that the sequence of operations in the execution of the instructions is carried out. Okay, we'll come to the details quickly. And within the CPU, the main components are the register file and the arithmetic and logic unit, in addition to the control unit. Okay, and then the data is typically available in the data memory, right? So we perform the read or write operations in the data memory to get the values of the memory operands. And after the processing is done, whenever the memory operand values have to be modified, then it involves the write operations, right? So typically this memory read and memory write operations for the data operands take place whenever the load and store instructions are present in the instruction sequence for a given higher level language program, whereas instruction memory is accessed whenever the instruction fetch needs to be done. So this is what we have discussed, and as I have mentioned, whatever goes on the CPU, that includes the control unit, arithmetic and logic unit, register file, the different special purpose registers, and some part of the memory, which is the fast memory like the cache memories. And again, typically there will be a separate cache memory for the instructions and the data, right? And these are what are called the first level cache memories. So the current the CPUs, the first level cache memory is also available within the CPU chip, and some process may have even the higher levels of cache memory in the process chip, which you will study in the next course. Okay, and whatever goes in the chip of the CPU is what is referred to as the microarchitecture of the CPU, and the design and implementation of this microarchitecture is the most crucial component in the design of the computer system. And how do you evaluate the performance of the CPU, for that matter, the whole computer system? At the highest level, we may look at how many programs get executed, right, and how much time it takes to execute the programs. That was what will be of interest. For that question to be answered, we need to understand several other issues related to the other modules in a typical computer system other than CPU, right, as we'll be maybe briefly touching upon later, right. The operating system plays a significant role in the performance of the that influences the performance of a computer system. Okay, we'll come back to that later. But in order to just evaluate the performance of a CPU, what we are interested in is how much time it takes to execute the sequence of instructions for a given program. And typically we specify the performance of the CPU, actually I would say the performance of the computer system, in terms of what is called the throughput at the lowest level. And the throughput at the lowest level is specified in terms of the number of instructions executed in a unit time, like a second. And in 60s and 70s, the performance used to be specified in terms of the millions of instructions per second. Okay, and nowadays it is specified in terms of the number of billions of instructions per second. That's called as the giga instructions per second, or simply called as the GIPS. Please remember that we are not specifying any particular type of instructions. It can be including the arithmetic and logic instructions, or it can be including the memory transfer instructions, or it can be control transfer instructions, right? And among the arithmetic and logic instructions, it can be simple logical instructions, or it can be integer arithmetic instructions, or the floating point arithmetic instructions, right? Typically, we specify the performance of the CPU in terms of the number of instructions per second, right? And how to quantify that is not a simple process. As once you understand how the instructions get executed, then we get an idea about the time that's likely to be taken for the execution of the instruction, right? So to specify the throughput in terms of number of instructions per second can be kind of only in terms of the average performance, which can be determined by executing several programs. And typically there will be what are called the benchmark programs, right, which will have the different mixes of the different types of instructions. And typically one looks at the throughput of a particular CPU or the computer system on these benchmark systems, benchmark programs, and then the performance specified in terms of this number of instructions per unit time. Okay, and typically when we say the processor throughput is 1 giga instructions per second, on the average, it's expected that every instruction will be executed in 1 nanosecond time if the clock frequency at which the processor operates is 1 gigahertz clock. Typically in the specification of computer systems, when you look at, right, they specify what is called the clock speed of the processor. Basically, the clock speed of the processor indicates the time available on the average for the execution of one instruction, right? Under the ideal conditions, we'll try to understand what are those ideal conditions quickly, right? So under the ideal conditions, typically one instruction can be executed in one clock cycle. And if the clock cycle period is 1 nanosecond, because if the clock frequency is 1 gigahertz, right, that's 10 power 9 cycles per second, then the clock period is 1 nanosecond. So is it possible to execute every instruction in the instruction set of the processor in 1 nanosecond time is the question that we want to understand, right? And in order to answer that question, we need to understand what is it involved in the execution of the instructions. Then we'll get some idea about how much time it's likely to take, what is the time taken to execute an instruction dependent on, and how do we kind of target the throughput of one instruction per clock cycle, that is 1 nanosecond for an instruction, right, is what we would like to get some idea about. Again, the more details will be discussed in the next level course. Okay. So as we were discussing in the last class, the typical way of this, I would say the simplest way of execution of instructions in a sequence of instructions given to as after the compilation of the high level language program is, let's say if there are n instructions, we assuming that there are no jump instructions in the call instructions, right? So the typical sequence of execution of instructions involves take the first instruction, go ahead and fetch that instruction, then execute that instruction. After you complete the execution of that instruction, then you start with the operations for the second instruction, and we continue this until we reach the end of the sequence. So this is actually the naive and the simplest way of the execution of the instructions, where we start with the operations for one instruction and then complete all the operations for that instruction before we start any operation for the next instruction. And what are these operations that we are referring to? Typically, the operations of operations in the execution of the instruction involve fetching the instruction from the memory, then figure out what is that instruction. That's what is called the instruction decode operation. And typically, any instruction may have one or more source operands to be fetched, and the source operands may be the register operands, and we need to fetch those operands from the register file. Then we need to perform the operation as specified by the instruction mnemonic, right? If it is in an arithmetic logic instruction, we need to perform the arithmetic and logic operation using the ALU. If it is a memory operation, like a load and store instruction, then we need to perform the memory read or memory write operation. So that's what is called the perform the operation state or the phase, right? And once you perform the operation, there will be some result that's produced by the ALU or the memory unit. Then we need to write the result into the destination operand. Typically, that will be a register for the arithmetic and logic instructions, and for the store operation also, store instruction also. I mean, the load instruction, the destination operand is a register. Okay, so these are the different operations that we need to perform in the execution of an instruction. Okay, so now let's try to understand what are the different components that are involved in the execution of the instruction and going through these different operations in the execution of the instruction. Okay. So if we take the instruction fetch, we have seen that just 1 minute, there's some problem. So the instruction fetch operation, as we have seen, typically involves getting the address of the instruction to be fetched from the PC, right? And the logic within the CPU will send that PC contents to the instruction cache. Let's not worry about how this cache is built and so on. It's enough if you understand that the instruction cache is a fast memory which is built using the static RAM cells, right? And typically the request for the instruction fetch will be sent to this cache memory first, and if that instruction is available in the cache, we take it from there. In case it is not available there, then we go to the memory. When we say the memory, it is the main memory. Main memory is built using the dynamic RAM cells, and typically the access times of this cache and the main memory will be different. So this may be less than 1 nanosecond, and this will be a few nanoseconds, maybe 20 nanoseconds. And if you look at the current day process, there will be multiple levels of this cache memory with the different access times, basically different speeds, right? Like there will be level 1 cache, level 2 cache, and level 3 cache. And the capacities of these caches will be different, as typically it will be very small for the level 1 cache, and it will be higher for the level 2 cache, and it will be even higher for the level 3 cache. And typically part of the content of the main memory will be available in these cache memories. And how that is done, again, we'll leave it for the next course. For the discussion in this course, it's enough if you understand that these cache memories are fast memories, and the time it takes to perform a read or write operation will be typically much less than 1 nanosecond period, right? And the main memory is much slower because it's built using the dynamic RAM cells, which are nothing but the capacitors where the data is stored. Again, I'm just only giving the very brief detail of that. Okay, but only important thing to note here is that the time taken to perform the read or write operations on the main memory will be much higher compared to this time taken to perform the operations in the cache memory. So once the address is sent, the memory module here, it will send the instruction by fetching the content of that memory location, and that will be taken by the instruction fetch module, and then it will pass to the next module called the instruction decode module. And this module will also perform the other operation called the operand fetch. And who takes care of the instruction decode? That will be done by the control unit. So whatever the instruction that's fetched will be sent to the control unit, which in turn will generate the different control signals. Again, we got some idea of this when we discussed the hack ALU and the hack CPU. Okay, and once the instruction is decoded and it figures out what is the type of instruction to be executed now, right? Typically, it will involve fetching some operands from the register file. So that will be done by sending the request for reading the contents of registers in the register file. So what will be sent to the register file? We'll send the register address, right? And what we get is the content of that register, which will be typically the data. Okay, and if there is only one read port, we'll read only one register at a time, right? Otherwise, if there are two read ports, we may perform the parallel read operations on the two registers in the register file. Okay, so the instruction decode stage has figured out what the instruction is, and then it has performed the fetching of the source operands. for the particular instruction that's going to be executed now. Then once we got the source operands, then we have to perform the necessary operations. That's what is called the perform operation stage, right? And what are the operations that we perform here? It depends on what is the kind of instruction that we are executing, right? So if it is the arithmetic or logic operations, right, then the perform operation stage will interact with the ALU. What is the interaction here with the ALU? It has to specify what is the operation to be carried out, right? So that will be done by specifying the opcode to that, and then it has to perform, or it has to send the operands, right? And then the ALU will perform the necessary operation or the specified operation on the operands. Then it will produce the result, and that result will be sent back to the stage which is dealing with this performing the operations. So this will be, I mean, ALU will be involved whenever we are dealing with the arithmetic or logic instruction. If it is a memory operand instruction like a load or store instruction, then again there will be interaction with the memory, but now there will be interaction with what is called the data memory. So in the first level, we will have the data cache. Then there will be part of the main memory where the data is stored, right? So whenever the memory operations are to be carried out, the address will be sent to the memory unit, right? Then if it's the write operation, the data will be sent to the memory unit. Otherwise, if it's a read operation, the data will be taken from the memory unit. Okay. So depending on the kind of instruction that we are dealing with, there will be an interaction with the arithmetic and logic unit or the data memory unit. And once this operation is complete, right, then typically we need to perform the write back of the result, right? And typically we are talking about writing into a register. So it is the same register file that we have referred to here in the second stage. So we'll send the register address and the data to be written, right? So that data will be written to that particular register. Okay. So typically these are the different stages that are involved in the execution of the instruction. We first fetch the instruction, then that instruction will be decoded. Then we fetch the source operands for that instruction. Then we pass on those operands to the ALU or to the memory unit. And then we perform the specified operation. And the result of the performing the operation will be written to a destination where the destination is a register by performing this write back result operation that involves writing into a register in the register file. Okay. So basically this diagram kind of indicates the flow within the CPU in the execution of the instructions, right? And what we now would like to understand is how much time it is likely to take to perform each of these operations at the different stages. Okay. So what is it involved in performing the instruction fetch? As we said, we take the content of the program counter, then send it to this instruction memory. And if it's available in instruction cache, then the operation may be completed in less than 1 nanosecond, right? That's within 1 clock cycle, right? Or it may take several clock cycles, like if it has to get from the main memory, which has access time of 30 nanoseconds, right? If my clock period is 1 nanosecond, right, then it will take several clock cycles to perform the main memory operation where I'm going to get the instruction from. Okay. So what we have to understand here is that if the instruction is not available in the cache memory, then the time that will be taken to perform this instruction fetch operation will be much larger, right, compared to the case where it's available in the instruction cache. Okay, actually that's where the design of this cache memory and then making sure that the instructions that are required for the execution of instructions are available for most of the time in the instruction cache is very, very important. And how that's done is what's going to be discussed in the next level course. Now, what is it involved in the second phase of this instruction execution? As we have seen, the control unit is fairly simple, right? In the sense, it does not take much time. Basically, it has to figure out the different fields in the instructions binary representation and then generate the control signals. Typically, this control unit will be a combination logic circuit, and the delay of this circuit will be dependent on the number of levels of logic gates, right, that are involved in the generation of the control signals, right? So typically that will not take much time. So the amount of time taken in the second stage is primarily going to be dependent on accessing the register file contents. And like we have seen, what is it involved in the accessing the contents of the register file? Basically, I perform the read operation. Basically, that involves using the read port. And earlier we've seen that the read port is nothing but a demultiplexer. So it's the delay of the demultiplexer. There's nothing more than that. Okay. So we see that this instruction decode and operand fetch stage does not take any significant amount of time, and that can be completed in less than 1 clock period time. Okay. Even if it involves fetching 2 register operands, right? And if I have only one read port in the register file, still it takes only the delay of the demultiplexer, right? And that is not significant as we have seen, because the delay of the demultiplexer is only few tau, right? Where tau is the propagation delay of the logic gate. So typically this second phase can be completed in less than 1 clock cycle period. Then when we come to this perform operation stage, where we are talking about either the arithmetic and logic instructions being carried out or the memory read and write operation to be carried out. Now, whatever we have done in the course so far should give an answer for this question. How much time it takes for the ALU to perform the operation? Yeah. Is it uniformly the same for all the arithmetic operations? When you say arithmetic operations, it can be integer arithmetic operations or the floating point arithmetic operations. Within integer arithmetic operations, it can be addition or subtraction or a multiplication or a division. And it can be an 8-bit operation or a 16-bit operation or a 32-bit operation or a 64-bit operation. If it's floating point, it can be on the single precision operation or a double precision floating point arithmetic operation. Right? Now, from the knowledge of how to design these arithmetic circuits, right? What will be your answer? How much time it takes to perform the specified arithmetic or logic operation by the ALU? What will it be? Will it be the same? Will it be the same for every instruction? Yeah, actually I'm waiting for a response from you people. No. Okay, that's what Vikram says. Right? It's correct. As we have seen, an integer odd operation, if it's a n-bit operation, right? We have seen that if it's a ripple carry adder, it takes 2 and tau, right? If it is a carry lookup order, right, then it takes a different amount of time. And if I use a carry lookup order with the higher propagating generate times, it takes a different time. So it all depends on which circuit is used. So typically in most of the process, one uses this n-bit adder using CLA based addition with the higher propagate and generate terms. And then you've seen that the multiplication operation will be different for the signed and the unsigned integers, right? And typically they are implemented using the sum and reduction methods, followed by the carry look ahead based addition, and we have seen that the amount of time it takes, let's say even for 32-bit multiplication, is not the same as the amount of time it takes for the 32-bit integer addition. So the time taken for the addition operation is different from the time taken for the multiplication operation, even for the same size integer operands. And the time taken for floating point arithmetic operations is completely different from the time taken for the integer arithmetic operations, right? So the amount of time taken for performing an operation by the ALU varies from one instruction to another arithmetic instruction, and accordingly, the logic in the control unit has to wait for that period of time for the result to come from the arithmetic and logic unit. And what we are interested in is whether the arithmetic and logic unit can complete the operation within one clock cycle period or not. Okay, if it is a 1 nanosecond clock frequency, it all depends on what is the propagation delay of logic gate and how many tau it will take to complete the necessary operation. Like what we have seen is that typical arithmetic operations may take of the order of a few tenths of tau, right? Like we have seen addition operation may take, integer addition operation may take about 15 tau or 20 tau. The multiplication operation may take about 40 tau and so on, right? Now it depends on what is this value of the tau. So the tau will be typically a few tenths of picoseconds, right? So now the total delay of the circuit is dependent on the time taken to complete the operation is dependent on what is the value of this tau and how many tau it takes to perform the necessary operation by using whatever the circuit that you have designed for performing the arithmetic operation, right? So now if we assume that all of that can be done within one clock cycle period, then it's fine. Otherwise, we have to have a mechanism to wait for that operation to complete and then take the result. Again, it will be responsible to the control unit, right, to monitor whether the specified operation is completed within the clock period time or not. Why this constraint of clock period, will come to that quickly. Okay. Yeah. So the time taken to perform this operation is very critical, right, in controlling the sequence of operations here. And similarly, accessing the memory to perform the memory read and write operations depends on whether those variables data are available in the cache memory or in the main memory. So depending on the where it is present, the time taken to complete the operations will be different. And the final write back stage is going to take a fixed amount of time because we are always writing into a register, and writing into a register basically involves the write port delay, and we have seen that the write port is nothing but a typical multiplexer and a decoder, right? And that does not take significant amount of time. Okay, so now let's assume that in order to understand the throughput of a processor, each of the stages, now I'll use an abbreviation for each of them, right? IF stands for instruction fetch stage. Then instruction decode will involve both decoding the instruction and fetch the operands. Then the perform operation will be performing the operation in ALU or data memory, right? And then finally, WB stands for the write back the result. Okay, so typically each of these stages will take certain amount of time. Let's say I call it as TIF, TID, and TPO. TWB. Now, what is the total time taken to execute the instruction now? So let me call it as capital T, right? So that will be the sum of all of these. right? So capital T denotes the sum of the time taken for operations in each of these stages. All right. Now, for a particular instruction IN, the time taken to execute this instruction, if I refer to as Tn, right? Will the Tn be same for the different instructions? Yeah. Assuming that, I mean, even to make the things simple, right? Let's assume that the instructions are available in the I cache and the data in the memory is also available in the D cache, right? Is it guaranteed that, or is it possible to assume that the Tn is the same for all the instructions? Irrespective of what type of instruction, is the Tn fixed? The Tn is not fixed. Okay, so the Tn will vary depending on mainly what operation needs to be performed in the execution of the instruction. All right, and even with the assumption that the time taken for the other stages is uniformly the same, right? The time taken to perform the specified operation will not necessarily be the same for the different instructions, right? Therefore, this capital T value will be different for the different instructions. Now, how do I find out what is the time taken to execute the complete instruction sequence? It will be the sum of this Tn over all the instructions. So the total time taken for the sequence of n instructions will be summation of this Tn over small n. And what will be the throughput now? I mean, the throughput can be specified in terms of the average time taken. That will be nothing but yes. And if you take the inverse of this, right, that will give the throughput. That is how many instructions can be completed in a unit time. Right. So this is how one can derive the throughput of a particular processor or a system, right, in the execution of the given sequence of instructions. Again, when you change the sequence of instructions, the different programs may have possibly the same number of instructions, but the instructions that are present in the sequence of instructions can be different. So for the different sequences, this summation Tn will be different. Therefore, the total time taken will be different. Therefore, the average time taken will be different. Therefore, the throughput of the processor will be different. Okay, that's why it's not easy to answer the question, right? What will be the throughput of a CPU or the throughput of the system, right? Unless we specify for what programs we are talking about the throughput of the system. That's why we are generally, when you want to compare two different systems, right, we have some benchmark programs which will have the mix of different types of instructions, right? And then we evaluate the time taken for the execution of these benchmark programs, and then say that for these benchmark programs, this is the throughput of the CPU or the system that you have designed. Okay. Now, if we just assume that each of these stages will take only 1 nanosecond, that is 1 clock period, right? Which is not really the case, but even if we assume that it will take 1 nanosecond time, right? And what will be this Tn now? Now Tn will be, for any instruction, it will be 4 nanoseconds, right? And what is the throughput now? Yeah, 1/4 nanoseconds. What does that basically mean? Yeah. How many instructions per second we will be able to complete? It will be 10^9/4. Right? And if I want to say in terms of how many instructions per clock cycle, and that will be denoted by IPC, which stands for instructions per clock cycle. Okay, so right now the throughput is 1 instruction per 4 clock cycles, right? Because it takes 1 clock cycle period for each of the stages, right? So total it takes 4 clock cycles. So we can say that 1 instruction gets completely executed in 4 clock cycle period. Okay, and typically this is not going to be acceptable, and one would like to target the throughput of 1 instruction per clock cycle, right? And that's what will be done in what is called the pipelined processors, which will not follow the sequential execution of the instructions, right? Which will follow the principle of what is called the overlapped execution of the instructions. What do you mean by the overlapped execution of instructions? Can we go ahead with the execution of second instruction even before the first instruction is completely executed, right? So can we start the operations for a particular instruction even before all the previous instructions are completely executed, right? So to answer that question, let us look at the structure here, right? What are the different parts of the CPU that are involved in performing the necessary operations in each of these stages? Like we see that in the instruction fetch stage, what we need is basically the I cache. Then in the instruction decode stage, we need the control unit and the read ports of the register file. And in performing the operation, we need the ALU and the D cache. And in the write back stage, what we need is only the write port of the register file. Is there anything that's common to each of these, any of these stages, any 2 stages? Is there any common component, right, that's involved in the performing the operations in each of these stages? We see that no 2 stages use the same component, right? Instruction fetch uses different components. The instruction decode stage uses a different component. Perform operation stage uses different components, and so on, right? So now that raises a basic question: why should I wait for the current instruction to be completed before I start the operations for the next instruction? Okay, and that's where we have a significant deviation from this conventional sequential execution method. Now, in order to understand this overlapped execution, let us try to understand what happens in the different clock cycles in the overlapped execution. Suppose I take instruction I1, I start with the operations for this. So let's say I complete the instruction fetch operation in the clock cycle 1. Then we go to the instruction decode stage in the clock cycle 2. Then we perform the operation in the clock cycle 3. Then we perform the write back in the clock cycle 4. If each of these operations for this instruction 1 is done by different components, can I get started with the operations for instruction 2? Normally, in the sequential execution, when would I start? I will start only in the clock cycle 5, right? So now what we want to understand is, can I do the instruction fetch for the instruction 2 in the clock cycle 2. What does that mean? When the instruction 1 is being decoded and the operands are being fetched for that, can I go ahead and fetch the instruction 2, right? Because the components that are involved in the two operations here are completely different, right? We can go ahead and perform both these operations simultaneously, that is in parallel, right? And then in the clock cycle 3, while I'm performing the operation for the instruction 1, right, then I'll go ahead and perform the decoding of the instruction for the instruction 2, right? Then in the clock cycle 4, when I'm writing the result back for the instruction 1, I'll start the operations for the perform operation stage in the instruction 2, right? Then it'll go to WB here, right? So now you can see I can do the operations in an overlapped manner for the different instructions. Right? So now how many clock cycles it will take to complete all these 4 instructions? We see that at the end of the clock cycle 7, right, we have completed the necessary operations for all the 4 instructions. If it is a normal sequential execution, right, it would have taken 16 clock cycles. Now we see that we are able to complete the operations in 7 clock cycles. And now I want you to answer, if I have n instructions in the sequence, right, how many clock cycles will be required to perform the execution of these instructions in a overlapped manner if the overlapped operations are going to be like what we have seen. Like if I have one more instruction, right, I'll start the instruction fetch in the clock cycle 5, decode in the clock cycle 6, right, perform operation here, and the WB here. That is the clock cycle 8. So we see that when the number of instructions is 4, it is 7 clock cycles. When the number of instructions is 5, it is 8 clock cycles. You can easily verify that it will take n plus 3 clock cycles to complete the execution of n instruction in the overlapped manner. Now, what is the throughput? It is n plus 3 clock cycles for n instructions, right? So this will be the number of instructions per clock cycle, and typically n will be much greater than 3, right? So now we can see that we can achieve a performance throughput of 1 instruction per clock cycle by simply going from the sequential execution paradigm to the overlapped execution paradigm, right? And now you can understand why it's called the pipeline. What do you mean by pipeline? Like if you look at any factory pipeline, when you're manufacturing a product, typically you don't wait for one unit of product to be completely manufactured before you start with the operations for the next unit to be manufactured, right? And it will go in a overlapped manner, right? In the same way here, right, we go through the operations for the different instructions in a overlapped manner. Only thing is we require some more logical support for this, right? We'll not spend time on that because that requires a lot more discussion to be done. So you'll study that in the next course, right? But most important thing here is that assuming that the required support is there, right, we can perform the execution of the instructions in an overlapped manner to realize this ideal throughput of 1 instruction per clock cycle. But please remember that this is only under certain assumptions, under what are called the ideal conditions. What are these ideal conditions? I'll just close this, right? Operations in every stage can be completed in 1 clock cycle time. Right? And if you really pay attention to it, we are making a lot of assumptions about the relations between the different instructions, right? So I'll just briefly mention the terms here, right? These are what are called the dependencies among the instructions. I'll briefly explain that in the next class. All right. And right now we are, right now we assume that there is no dependency, which may not be true, right? And also we assume that there are no iterations here and there are no control transfers here, right? So we assume that there is no what is called control dependencies. Okay. So under these assumptions, it's possible to realize the throughput of one instruction per clock cycle in the pipeline processors where the overlapped execution of the instructions take place, right? But in a practical scenario or in a real scenario, right, none of these assumptions need to be valid, okay, always, okay, only sometimes it may be valid and sometimes it can't be valid. And in that case, the throughput will be less than this one instruction per clock cycle because it will take more number of clock cycles to execute the n instructions. Okay, maybe I'll stop at this point. Are there any questions? Okay, maybe we'll stop now. We'll continue it in the next class tomorrow. Okay, bye.